Slide 1. Tides, Topic 07A, Part 2, The Bulge Theory of the Tides. The bulge theory of the tides is the simplest, but not the best, theory of the tides. There are several theories of the tides. The bulge theory of the tides is better known as the equilibrium theory of the tides. It was the first good theory of the tides and was created by Isaac Newton with his theory of universal gravitation and laws of motion. As is common in science, Newton made simplifying, but unrealistic, assumptions when trying to understand the basic issues of the phenomenon. Otherwise, you get bogged down with details. For example, the bulge theory assumes that there are no continents and that the ocean floor is perfectly flat and very deep, far deeper than 2 miles. The bulge theory makes accurate predictions about the number and approximate timing of tides. There are 2 high tides per day, 2 low tides per day, and it takes about 6 hours for a high tide to become a low tide and vice versa. In addition, the bulge theory does a pretty good job predicting the relative sizes of the tides. However, it cannot be used to calculate the actual time and height of the tides with much precision. It is off by a few hours and a few feet much of the time, because of the unrealistic assumptions. Nonetheless, in this class, we will study the bulge theory of the tides, because it is the simplest theory of the tides which captures the basic causes of the tides. Slide 2. What is the bulge theory of the tides? How does it work? According to the bulge theory of the tides, there are 2 bulges in the ocean, places where the sea surface is higher than normal. The bulges are on opposite sides of the Earth. One bulge points towards the Moon, and the other bulge points away from the Moon. The water that makes the sea surface higher at the bulges comes from the other 2 sides of the Earth. It has to come from somewhere, which lowers the sea surface at these locations. The 2 places where there is more water and the sea surface is higher, the bulges, are experiencing high tides, and the 2 places where there is less water and the sea surface is lower are experiencing low tides. Thus, at any moment in time, 2 regions on opposite sides of the Earth are experiencing high tides, while the 2 regions between them are experiencing low tide. Slide 3. 2 bulges equals 2 high tides per day. 2 bulges in the Earth's ocean results in 2 high tides and 2 low tides per day, with 6 hours between high and low tide. Each day, the Earth rotates on its axis, spins all the way around one time. The bulges stay facing the Moon and facing away from the Moon as the Earth turns underneath. As a result, each day every location on the Earth goes into a bulge, high tide, then out of the bulge, low tide, then into the other bulge, high tide, and then out of the bulge, low tide. Thus, each location on the Earth experiences 2 high tides and 2 low tides per day. It takes 24 hours, 1 day, for the Earth to turn all the way around, so it takes 6 hours for the Earth to turn a quarter, 1/4, of the way around, and therefore for a location to move from a place in a bulge, high tide, to a place outside a bulge, low tide, or vice versa. For example, in the diagram on the slide, picture number 1 shows an island, the brown triangle, underneath the Moon in a bulge. It is high tide at the island. In picture number 2, the Earth has rotated 1/4 and now the island is outside of a bulge, and it is low tide at the island. In picture number 3, the Earth has rotated 1/4 again, and the island is in the bulge on the side of the Earth facing away from the Moon. It is high tide at the island again. In picture number 4, the Earth has rotated another 1/4, and now the island is outside a bulge and at low tide again. Note, the Earth moves, not the bulges or the Moon, in this explanation. Slide 4. The Moon's gravity pulling on the ocean creates one bulge. Anyone with a basic familiarity with gravity may be confused by the claim that there are 2 bulges in the surface of the ocean. Gravity is an attractive force. All objects in the universe are attracted to all other objects in the universe. So you feel a gravitational attraction towards your phone, your teddy bear, your car, pencils, chairs, tables, rocks, paper, trees, men, women, dogs, sheep, and so on. Oh, and they are gravitationally attracted towards you too. The strength of the attraction depends upon the mass of the objects and how far apart they are. The heavier the objects, the more mass or material stuff they have, the stronger the gravitational attraction. The farther apart the objects are, the weaker the gravitational attraction. For example, the Earth exerts a stronger pull on me than a person or anything else nearby, because it is much more massive. So when I jump, the Earth's strong gravitational attraction pulls me down towards it. The Earth also exerts a stronger pull on me than the Sun, but only because I am closer to the Earth than the Sun. Even though the Sun is much more massive than the Earth, the Sun is also much farther away from me than the Earth. There is one final rule for gravity: the objects feel exactly the same attraction for one another. The attraction is mutual, equal, and in opposite directions. Thus, the Earth is attracted to me exactly as much as I am attracted to it. When I jump, I'm pulled down a lot more than the Earth is pulled up, because I'm much less massive, easier to push around. Similarly, if you go up to a person and give them a push, you could probably knock them down, but if you give the same push to a car, it is not going anywhere. The car is much more massive than the person, so the force of the push has a much smaller impact on it. Slide 5. The Moon's gravity pulls on the ocean water, pulling it towards the side of the Earth that the Moon is on and pulling water away from the other side. As you can see in the picture on the slide, this only causes one bulge in the surface of the ocean. As one day passes, every location on the Earth would go into the bulge, high tide, and then out of the bulge, low tide, leading to one high tide and one low tide each day, 12 hours apart. Clearly this is wrong, because we observe 2 high tides each day and 2 low tides each day. What causes the other bulge, the one on the side of the Earth facing away from the Moon? We must be missing something. Slide 6. The Moon's gravity pulls on the Earth, causing it to orbit the barycenter. Not only does the Moon's gravity pull on the ocean water, it also pulls on the Earth. The Moon's gravitational pull is strong enough to move the Earth a little. The Moon's gravitational pull on the Earth is something like a person pushing on a parked car. If you push a parked car, it won't go anywhere because your push is too weak, but you can make it rock or wiggle a bit. The Moon's gravitational attraction makes the Earth do a small orbit around a place we call the barycenter, the X in the picture on the slide. Barycenter means heavy center. This place is called the barycenter because the Earth orbits this place as if there were a heavy object there. The orbit is so small that the barycenter is always inside the Earth. Note that the barycenter is just our name for a location. The barycenter itself does not exert any pull on the Earth. Examine the picture on the slide. The Earth goes around the barycenter over the course of a month just as the Moon goes around the Earth, and the barycenter, during a month. The Earth and Moon are on opposite sides of the barycenter during their orbits. Slide 7. Of course, the Earth also orbits the Sun, so both motions, the Earth's motion around the barycenter and the Earth's motion around the Sun, are happening at the same time. The result is to make the Earth wiggle back and forth in its elliptical orbit around the Sun. Slide 8. The other bulge, water, sloshes away from the Moon due to the Earth's orbit around the barycenter. The ocean's water also goes around the barycenter with the Earth, but the ocean's water is not solid, so it sloshes around. If you think of your own experiences going in a circle, you know that objects get flung towards the outside, away from the center of the circle. For example, think about your experiences riding on a merry-go-round or that amusement park ride where you stand against a wall and as it spins, you are pressed up against the wall. Better yet, do the experiment described below. In the same way, the water on the Earth gets flung away from the barycenter, and the Moon, owing to its orbit around the barycenter, causing a bulge on the side of the Earth away from the Moon and creating the second bulge. Experiment: fill a clear bottle with some liquid, about halfway or less, or just go get any partially empty, clear bottle out of your refrigerator. Now, spin in place and watch the liquid. Notice how it moves away from you, away from the center of the circle. If you are really daring, put a little water in a bucket and spin the bucket really fast forward, up, back and down. If you spin it fast enough, the water won't fall out. You can do this experiment at home, but I recommend that you do it outside just in case. Slide 9. 2 bulges, putting it all together. Someone who has been paying attention might say, wait a minute, don't the two effects cancel one another out? Won't the stronger one win, resulting in just one bulge? The answer to this question is no, the two effects do not cancel, because the Earth is very large and water is a liquid, not a solid. Recall that the farther apart two objects are, the weaker the gravitational attraction is. Thus, the Moon's gravity exerts a stronger pull on the ocean water on the side of the Earth close to it, and a weaker pull on the ocean water on the far side of the Earth. On the side of the Earth closest to the Moon's gravity overcomes the tendency for the water to get flung away from the barycenter, creating a bulge towards the Moon. On the side of the Earth away from the Moon's gravity is not strong enough to hold the ocean water in, so it gets flung away from the barycenter, creating the second bulge. Thus, it is accurate to say that the Moon's gravity causes the tides. Note that it is the Moon's gravitational pull on both the ocean water and the Earth, which causes the small orbit around the barycenter, that results in the tidal bulges. Also, it is not just the strength of the Moon's gravitational pull that determines how large the bulges become, but how different the strength of the pull is on each side of the Earth. As we will discuss soon, the Sun also affects the tides. The Sun clearly exerts a stronger gravitational pull on the Earth than the Moon, because the Earth orbits the Sun. Even though the Sun is farther away, the Sun is much larger than the Moon. However, each side of the Earth is about the same distance from the Sun, so there is a much smaller difference in the strength of the Sun's pull on the ocean water on each side of the Earth, resulting in a smaller effect on the tides. In other words, the tendency of the water to move away from the center of the Earth's orbit around the Sun is almost equal to the Sun's gravitational pull on the water on both sides of the Earth. In short, the Sun's gravitational pull on the Earth and its ocean is stronger than the Moon's gravitational pull, but the Sun's gravity has a smaller effect on the tides because the Sun is much farther away from the Earth than the Moon. Which bulge is larger? Both effects cancel out at the center of the Earth, midway between the two bulges, so the two bulges are the same size. Slide 10. Why the tides get later by about an hour each day. It takes the Moon about a month to orbit the Earth, so in a single day the Moon moves a little, about 1/30 of its orbit. If a location is at high tide, beneath the Moon, and then the Earth spins one time all the way around, one day passes, the location will not be underneath the Moon again and at the high point in the bulge, because the Moon and bulge have shifted a little bit. See the diagram on the slide. The Earth, Moon, and bulges on the left represent the starting point, a high tide at the brown triangular island. The middle picture shows their relationship after one day, one rotation of the Earth. The Moon has moved through a small part of its orbit and the bulges in the ocean have moved with it, so the island has not quite reached high tide. The Earth needs to turn a little bit farther to bring the location of the island underneath the Moon and thus to high tide. The last picture on the right shows how a little extra rotation by the Earth will allow the island to catch up with the Moon and the bulge. How long does it take the Earth to catch up with the Moon? Well, if the Moon goes through 1/30 of its orbit, then the Earth needs to turn 1/30 more, which is 24 hours divided by 30, which is 4/5 of an hour or 48 minutes. By the way, we call a day plus the amount of time it takes for a spot on the Earth to come back underneath the Moon a lunar day. You may recall that in Unit 7A-1 I said that tides are about an hour later each day. 48 minutes is the more accurate estimate. 48 minutes is the average amount by which tides are later, which means some days tides are even later and some days they are not as late. In other words, some days tides are as little as 20 or 30 minutes later than the day before them. Some days tides are as much as an hour and 20 minutes later than on the previous day. One important reason why is because of the influence of the Sun on the tides. Slide 11. Spring tides and neap tides. Recall that spring tide conditions are when the tidal range is large, high tides are very high and low tides are very low, and that spring tides are strongest at new moon and full moon. Neap tide conditions are when the tidal range is small, high tides are not very high, and low tides are not very low, and that this pattern is strongest during half moons. Spring and neap tides result from the sun helping the moon create the tides or working against it. Like the moon, the sun tries to create two tidal bulges, one towards the sun and one away from the sun. However, the sun's effect on the tides is smaller than the moon's effect, about 1/2, so the moon always wins the fight with the sun to determine where the two tidal bulges will be. In other words, the moon determines where the high tides and low tides will be. The sun, however, influences how high the high tides are and how low the low tides are. Slide 12. Notice that spring tide conditions are strongest when the Earth, Moon, and Sun are all in a line, new moon and full moon. Under these conditions, the Moon and Sun are trying to create high and low tides in the same places. Remember, they both try to make a bulge on the side of the Earth facing them and the side of the Earth facing away from them. Thus, the Sun is helping the Moon pull water from the low tide places to the high tide places, making the high tides higher and the low tides lower. Neap tide conditions are strongest when the Earth, Moon, and Sun are in an L-shaped formation, with the Earth in the corner or bend in the L. Under these conditions, the Moon and Sun are working against one another. The Moon is trying to create bulges towards and away from the Moon, and the Sun is trying to create bulges towards and away from the Sunday. Because the Moon has a stronger effect on the tides, it wins, and the high tide bulges face towards and away from the Moon. However, the bulges are unusually small, because the Sun is pulling water from the high tide places to the low tide places, making the high tides lower and the low tides higher. Slide 13. Let us review what we have learned about spring tides and neap tides. Sometimes the Moon and the Sun both want high tides and low tides to happen in the same places at the same time. In other words, the Moon's and Sun's gravitational pulls are working together. This makes high tides higher and low tides lower. Spring tides is the name we give to these time periods when high tides are higher than normal and low tides are lower than normal. Sometimes the Sun wants it be high tide where the Moon wants it to be low tide, and vice versa. In other words, the gravitational pulls of the Moon and Sun fight about where high tide and low tide should be. The Moon always wins in these fights because it is closer to the Earth, and so the Moon mostly determines where high tides and low tides will be. But the Sun interferes a bit, pulling up the low tides, and pulling down the high tides. Neap tides is the name we give to these time periods when high tides are not very high and low tides are not very low. Slide 14. Other factors that affect the timing and height of the tides. There are many more features of the tides that can be explained using the bulge theory of the tides. For example, in the mid-latitudes, the first high tide of the day may be higher than the second high tide of the day, or vice versa. This is caused by the fact that the Moon's orbit does not keep it over the equator. The Moon orbits at an angle to the equator, as we saw at the end of Unit 07A-1. So, sometimes the Moon is above the equator and sometimes it is below the equator. Thus, the Moon's gravitational pull shifts the bulges, making one bulge larger north of the equator and one bulge larger south of the equator. As you might imagine, the larger a bulge is in a hemisphere, the higher the high tide it creates, and the less of a bulge there is in a hemisphere, the smaller the high tide it creates. In the diagram below, both people are in the northern hemisphere. Person A is where a tidal bulge is shifted northward and thus is experience the larger high tide at the moment shown in the diagram. Person B is experiencing a high tide, since they are on the side of the Earth where there is a tidal bulge. However, much of the bulge is shifted into the southern hemisphere so their high tide is not very high. Slide 15. Another example is king tides. King tides are the highest high tides of the year. There are several factors that produce king tides. I have treated the orbits of the Earth and Moon as circles, but really orbits are elliptical, oval-shaped. This means that sometimes the Moon is a little closer to the Earth and sometimes the Moon is a little farther from the Earth. When the Moon is closer to the Earth, its gravitational pull is stronger, so more water is pulled into the bulges. In other words, more water is pulled from the low tide spots on the Earth to the high tides spots, leading to higher high tides and lower low tides. The same is true of the Earth's orbit around the Sun. The Earth is closest to the Sun in January and farthest from the Sun in June. Thus, the Sun's gravitational pull is strongest on the Earth and the ocean in January. It will add its pull to the Moon's gravitational pull during spring tides in January. Thus, the largest king tides will occur in January during full moon or new moon, spring tides, when the Moon is at the closest point in its orbit around the Earth. All three of these, January plus the correct moon phase plus the Moon at closest point in its orbit, do not all happen at the same time every year, so when king tides happen and how big they are vary from year to year. King tides will happen when two of the conditions are more or less met and the third is pretty favorable. For example, a king tide might happen in February if the Moon is nearly at the closest point in its orbit during a full moon. In this example, the Moon's orbit and phase are excellent, and the Earth is pretty close to the Sun, since February is only 1 month later than January. At the moment, I suspect your brains are probably full when it comes to the bulge theory of the tides. Now that we have discussed an oversimplified explanation of tidal patterns, we will look at how real tides behave in the next unit.